In today's module, we will start with the state space model. We will first define what the state space model is and then discuss why it is of importance. We will look at the importance of the state space model through some examples. As you will see that most of the standard models like the classical models and the Box-Jenkins models come out as special cases of the state space model. Hence, if we can analyze the state space model, it will be possible to analyze these classical models or the Box-Jenkins model through the techniques that we will be using in the state space model. The state space models were originally developed by engineers to control linear systems. However, later these models became very popular in time series as well. This is because the model enveloped most of the linear models, primarily the classical and the Box-Jenkins models. Therefore, it can be taken to be a omnibus model for most time series. Now, the state space model can also be looked upon as a latent variable model, since the underlying structure of the series which is observed is often modeled through unobservable variables. So, there will be variables involved which we do not observe, and the variable that we observe can be written in terms of these unobservable variables, and that is how we actually formulate the model. So, let us take x t as the observed time series, and suppose we have observations at t equal to 1 to n. Now, the first set of equations that we formed are referred to as the observation equations. How do you do this? Let x t be a function of d random variables w t. This is a vector consisting of w 1 t, w 2 t up to w d t. So, there are d variables involved in this random vector. We call this vector w t the vector of state variables. Now, like x t, this vector occurs at t, but unlike x t, we do not observe this. So, this is a latent variable, unlike x t, which is manifested and which can be observed. Now, let alpha equal to alpha 1 to alpha d be a vector of constants. Then we will write the observation equation as x t is equal to alpha prime w t plus epsilon t, where epsilon t is, as always, the white noise sequence with mean 0 and variance sigma epsilon square. So, we have defined the observed variable in terms of the latent variable in this model. Then we have a second equation. We will call this the state equation. To define this, let eta t be eta 1 to eta t n, be IID random vectors with mean 0 and dispersion matrix sigma, which is a diagonal matrix. And we will assume that expectation eta t eta s prime is equal to 0 for t not equal to s. Let phi and k be two matrices of parameters. So, we have two parameter matrices, and what we do is we write the state equation as w t is equal to phi w t minus 1 plus k eta t. Notice that this looks like a AR1 type of model. So, w t is modeled by w t minus 1 and eta t in this case is the error, and we have an error coefficient in this case, and phi is the basically the autoregressive parameter. So, it looks like the autoregressive model, but unlike the autoregressive model which is on the observed variables, these are on the latent variables, and neither w t nor w t minus 1 of course is known. We will also in most cases assume that epsilon t and eta t, that is the two errors, epsilon t is the error in the observation equation and eta t the error in the state equation. These are mutually independent, and both of them are independent of the first state variable w 1. That is where we begin with the first observation that we should have had for the latent variable. In most cases also epsilon t and eta t would be assumed to be normal, but at this stage we do not require that. Now, let us look at a few examples which can be put in the state space form. Let us look at first the simplest of the classical model, the local level model. This is a series with no trend or seasonality. So, in this case xt has no trend or seasonality, and this we have encountered when we did the exponential smoothing. So, let us look at this model first. In this case, putting this into a state space model is very simple. We write xt is equal to Wt plus epsilon t, where epsilon t is white noise 0 sigma epsilon square. So, this is the observational equation that we have. Now, Wt in this case would be the mean level at time t, and we will say that Wt is generated from Wt minus 1 plus eta t, where eta t again is white noise. So, basically Wt is Wt minus 1 plus some error. So, what has happened at the previous state plus an error. Now, you can observe that this is a random walk, and let us look at an example where such models will work. Suppose we are looking at a manufacturing system, and suppose in a factory coins are being produced, and what is xt? Xt is the diameter of a coin that we are looking at. So, we want the diameter to be fixed at certain level. So, we will be observing the diameters at different time points as the process moves along. Now, the diameter of a coin produced at time t would depend on what the process level of the machine at the time is at, but we are not observing the process level. So, this is latent, and this is manifested through the diameter of the coin, which is your xt, and that is what we observe. So, xt is given by Wt, and maybe there will be some errors in observation. So, it is Wt plus epsilon t, and the process level would depend on the process level at time t would depend on what the process level at the previous time point was, and we can expect this to be a random walk, and hence we can apply the state space type of model to this, with the first equation as the observation equation and the random walk of Wt is the state equation. So, this is how a local level model can be expressed in the state space form. Now, if you observe here, Zt is delta xt, which is the difference, first difference of xt and xt minus 1, and this becomes eta t plus epsilon t minus epsilon t minus 1. Then you can see that since the right hand terms are all errors and they have expectation 0, expectation Zt is going to be 0. And if you calculate the autocorrelation function of Z, then you get this as rho Zh comes out to be minus sigma epsilon square by twice sigma epsilon square plus sigma eta square, provided h is equal to 1, and it is always going to be 0 for any h greater than 1. Now, remember that this is how the ACF of a MA process looks like. So, we can justifiably think that Zt is MA 1. Now, mind you, Zt comes out as a result of differencing xt once, and hence xt must be a ARIMA model with p equal to 0, one difference, that is d equal to 1, and a MA1 process, therefore q is equal to 1. So, in fact, we can write this as a ARIMA 011 model, and hence we can see that there is also a relationship between the ARIMA model and the state space model, but we will look at this in greater detail as we go along. Now, let us look at the next model. This is the local linear trend model. So, in this case, we assume that there is a trend, but there is no seasonality. So, we model as xt is equal to W1t plus epsilon t as before. So, xt depends on the latent variable W1t, and W1t itself depends on W1t minus 1 and W2t minus 1 besides a eta 1t, and again eta t is white noise. And then finally, what we have is W2t is equal to W2t minus 1 plus eta 2t. We have 3 equations now. We had 2 previously, and we have a new additional one. Let us explain this. So, xt depends on the latent variable W1t, which is unobservable, but which occurs at the time t. and this W1t is composed of two things. Firstly, it is the mean level, and this mean level is given by the mean level at the previous time point, that is W1t minus 1 plus the trend in between these two. So, the trend at t minus 1 added to the mean level at t minus 1 gives you the mean level at the time point t. This is the first equation that we get, the state equation, and the second state equation is that the trend actually, or the slope, would be increasing with t. So, we have W2t is equal to W2t minus 1 plus eta 2t. So, it is increasing and it depends on what the trend was at the previous step. So, in this case we have two latent variables, W1t is the mean level and W2t is the slope, and we can formulate the state equations as Wt is equal to, this is your phi matrix 1 1 0 1 Wt minus 1, we are taking k to be equal to 1 and we have the errors as eta 1t and eta 2t. So, the first equation xt is equal to W1t plus epsilon t is the observation equation, and this state equation we have in terms of these two variables. So, we can put this in the state space model form. Now, let us look at a basic structural model where we have both trend and seasonality. In this case, we model xt as W1t plus W3t plus epsilon t, and epsilon t again is white noise. W1t is the mean level and we will model it as before, that is W1t is given by the mean level at t minus 1 plus W2t minus 1, where W2 basically is the slope or the trend. So, again like the model before, this would be W1t minus 1 plus W2t minus 1 plus eta 1t, and the slope is given by W2t is equal to W2t minus 1 plus eta 2. It is again a random walk and it will depend on what had happened at the previous step plus an error. But in this model we have another variable, and this is because of the seasonality, that is W3t. Now, suppose there are S seasons and the seasonal effects are St, St minus 1, St minus S plus 1. Mind you, St minus S would be the same as St, because if you go back as seasons, you come back to the same season and you have only one seasonal effect standing for the season over different years. Also, we have the condition that the seasonal effects sums up to 0. So, there will be some plus effect, some minus effect in an additive model, and this will sum up to 0. Now, if we have this, then we can write St in terms of the other seasonal effects as minus summation j equal to 1 to S minus 1 St minus j, and we will add a error to this case eta 3t. So, you see that we have a little bit more flexibility. We do not say that the seasonal effects sum up to 0, but there may be a little bit of error involved and we model that through eta 3. And then if we look at the state variables as W1t, W2t, and then we take St, St minus S plus 1 etc., then we can write this in the state equation form as follows. So, the vector on the left is the state variable, then we have phi, then we have this lagged variable, and then we have the error. So, this is again how you can write the state equations and the basic structural equation in the state space form. Let us move to the Box-Jenkins model. Let us start with the ARP model. We have xt is equal to alpha 1 xt minus 1 etc. up to alpha p xt minus p, and the white noise term epsilon t. In this case, let us write Wt as xt minus p plus 1, xt minus p plus 2 up to xt. So, primarily this is a p-dimensional vector, and we will also define alpha and k as two vectors which are 0 0 etc., and only the last element is equal to 1. Now, having done this, we define phi as follows. So, if you look at phi, it has the first column except the last row. Last row has all the AR parameters. The first column is, barring the last row, is 0, and barring the last row, the other columns give us the identity matrix. Now, if you write phi this way, it is easy to see that xt can be written as alpha prime wt, because if you multiply wt by alpha prime, then it just picks up the last element, which is xt, and hence we get this. And also, if you write wt is equal to phi wt minus 1 plus k epsilon t. Now, k epsilon t, what does it do? It picks up the element epsilon t only for the last equation. And what about the remaining equations? The remaining equations basically becomes identities. So, xt minus p is picked up from wt, the first element of wt. On the other side, you have phi wt minus 1, wt minus 1, in that xt minus p plus 1 comes as the second element, and your 0 1 0 0 vector picks the second element up. So, this becomes on either side xt minus p plus 1, and similarly this goes up to xt minus 1. So, all the other elements in wt in the second equation, the state equations, are primarily identities, where we have on the left hand side xt minus j, on the right hand side also xt minus j, and only the last equation gives us xt is equal to alpha 1 xt minus 1 plus alpha p xt minus p plus epsilon t. That is the AR model. So, we can write the AR model in the state space form. Now, let us move to the ARMA PQ model. In the ARMA PQ model, we have both the AR component, which is alpha 1 xt minus 1 to alpha p xt minus p, plus the MA component, which is epsilon t, beta 1 epsilon t minus 1, beta q epsilon t minus q. Assume that we may take a coefficient of epsilon t as beta naught, which will be primarily 1. Now, we can write this in terms of the characteristic functions as phi b into xt is equal to psi b epsilon t. Now, let us define the state variables wt as phi b wt is equal to epsilon t. In that case, you can see that phi b xt would be psi b wt, and if you take the inverse of phi b, this becomes xt is equal to psi b wt. And if you write this out in this following form, then you have xt is equal to beta r minus 1 to beta naught, wt minus r plus 1 to wt, and that is equal to alpha prime wt. So, our betas, which is in the psi b part, can be spread out as the alpha vector here, and the wt's can be written, we can write the wt's in the vector form as wt minus r plus 1, t minus r plus 2, etc. up to wt itself. So, it gives us the wt vector, and therefore, xt is equal to alpha prime wt, and then you have the error component, and we get the observation equation. Now, if we look at the AR model, we then have from it wt is phi wt minus 1 plus k epsilon t, whereas before wt is xt minus p plus 1 etc. up to xt, alpha and k are 0 0 0 1 vectors, and phi is with the AR1 parameters as the last row. This is what we have done for the AR model, and hence we can use the same results for Wt, and we know that Wt in that case would be phi Wt minus 1 plus k epsilon t, which is the state equation. So, we can write the ARMA also in terms of the state space model. In fact, we can do the ARIMA also, that can also be similarly set up as a state space model. In fact, as I stated, most of the classical models and the Box-Jenkins model can be written as state space models. We will look at the state space model and see how we can estimate its parameter, and therefore, if you know how to do that, you will be able to solve most of this models, the Box-Jenkins and the classical models, either directly or through the state space setup. In today's lecture, we had been looking at the state space model. We defined the two equations which are the prime focus in a state space model, primarily the observation equation, which is based on the given series, and the state equation, which is primarily based on the latent variables. We saw through examples why the state space model is of importance, and what we found was that most of the classical models and the Box-Jenkins type of models can come out as a special case of the state space model. So, in subsequent lectures, we will be looking in detail at the state space model, so that if we can analyze this model, we will have a general way of analyzing most of the time series models.